Okay, all right, sounds good. So this is great. I'm really excited to be here, and my general sense is that the people who are, I mean, I can't see any of you right now because I'm not on Gather.Town for the duration of this talk. But my general sense is that the people who are attending the talk, they're often sort of teams that have participated in Formula Bharat before, but are now looking to transition to an EV powertrain, electric powertrain, right? So that's sort of the audience that I'll try to address in this talk, right? So this talk, just to be clear, will not go over the basics of Formula Bharat events, right? I'll assume that you sort of have some sense of what those events are like, things like endurance event, acceleration event, and so on. But I'll try to go from that point on in talking about how to think about designing your EV powertrain from there, right? So with that sort of introduction, let me share my screen and we will take off, right? So Kathy, I'm assuming you can see my screen,
Yes.
right? So again, I'll be available for a while after this talk in Gryffindor, I think. But my email address is on the screen. If you'd like to get in touch, either you can contact me over LinkedIn or over email, even later on, right? Now, before I go into technical details, right? Let's talk about why are we doing this, right? Why am I talking about starting from scratch on the EV powertrain? So the very first thing is, well, we would like you to transition to an electric powertrain like yesterday, right? I mean, at least I would, right? And there is, I mean, electric powertrains, electric vehicles are the future, right? If today you work on an electric powertrain while you're in college, 2 years from now, you can build a career in a growing, exciting sort of space. And so that's one great reason to start thinking about it now. Maybe you should have already done it. I've seen several great teams who have already transitioned over the last few years. The second important part is that an electric powertrain requires collaborative interdisciplinary work, which is not very common, at least in colleges. It's not something that you're naturally trained for, right? And so like the caricature of that is that, well, electrical engineers don't understand gear ratios that well. Mechanical engineers don't understand power factors or C ratings or stuff like that, right? But by the very nature of its construction, an electric powertrain involves deep competence both on mechanical engineering and on electrical engineering. Like you cannot get around that in any way. And therefore, so this is something to keep in mind as you design it, is that you are going to have to work very closely across disciplines, right? The third big thing is that electric powertrain design is sort of a large, complex design space. So for example, if you were doing IC engine vehicle, there would be, first of all, you would never think of designing an IC engine from scratch. You would probably just go buy something from outside. And there would be a relatively small set of options that you would choose from. In this case, motors are available in a wide variety of types, voltages, power. Battery cells are available in a variety of chemistries, form factors, C ratings. Battery pack design, right? So again, compared to IC engines where you just like fill it up with petrol or whatever, and it just works. Here you're going to have to design an accumulator, design and fabricate it, right? And if you're building sort of a lithium-ion battery pack, which is what most people do, that design and that fabrication is extremely complex, and there are very few people out on the street who know these things, right? So it's a and that is in part because the fourth point is sort of this is a nascent space, new technology, new ecosystem. So there aren't enough skills among your team. In some cases, there may not be adequate skills among your professors. There are certainly very, very few people who there are very few shops in the market where you could just show up and ask questions that will answer them right away. It's not clear where you get components from. The components can be of varying quality, and you have sort of difficult buy versus build decisions, right? Like, should we build our battery pack ourselves, or should we ask a small company to build it, or should we buy something off the shelf, right? So for all of these reasons, it's important to think through these design decisions, or this exercise of switching to an electric powertrain carefully from the get-go, right? Now, in my mind, right, the starting point has to be, what do you want to achieve as a team in this particular event or this particular competition, right? I mean, the competition has several events, and before you do any technical exercise, you have to start by saying, well, what is it that we as a team want to achieve for this year in this competition, right? And so, for example, in the reports, when teams write, they state very clearly things like, we want to complete the acceleration event within 5 seconds, or we don't want to have a longitudinal, we want to have a longitudinal acceleration of at least 1.2 Gs. Or it is also quite acceptable to say, we don't care about, all we care about is finishing the endurance event, right, for this year, right? We will do very well on the acceleration event, but we just want to finish the endurance event, right? So, but it's important to set measurable performance goals for each event, for your vehicle, right? Now, if you do that as a step one, and you do that fairly well, right, then that naturally leads to the exercise of sort of step two, which is translate your performance goals into technical requirements, right? And so, for example, if you want to do the acceleration event in less than 5 seconds, that means that for a vehicle of a certain weight, you have to produce at least a certain amount of torque, right? So that gives you a requirement on the peak torque that your motor must have, right? Or so now again, these are plots from a report from one of the teams last year, and the thing to focus on, right? Often in when we talk to teams, they obsess about peak torque, right? Whereas really the thing to think about is, what is the required torque and required torque at every speed that I'm going to achieve, right? So, for example, you could run a simulation, a lap simulation for the endurance event, and that lap simulation, if you say, well, I want to finish the endurance event in a certain amount of time, then that translates into a certain speed profile around the lap, which in turn translates into torque requirements, right? So you should start by plotting on a single plot the required torque at every RPM for the endurance event. Similarly, do the same exercise for the acceleration event and so on. So each of your performance goals from each of your events should translate into sort of technical requirements of torque and later on current and so on, right? And you have to sort of pay attention to the fact that there is no one number or one metric that alone is enough to satisfy all your performance goals, right? So, I mean, there is a reason why a motor has torque speed characteristic curves, right? Because the entire curve sort of matters, because the available torque at every speed matters, right? And so by plotting your required torque with RPM for, say, the endurance event or the acceleration event, etc., you will understand your technical requirements that your motor needs to satisfy, or motor means your motor plus drivetrain needs to satisfy, right? So that, in my mind, is sort of step two, right? Now, once you've done that exercise, right? So now you know at every RPM how much torque is required, right? So then the next part is, how do you design the motor plus gearbox to deliver that torque at that RPM at all times, right? So note here that the motor and gearbox sort of go together, right? if your motor has low torque, you can have a higher gear ratio, and vice versa, right? So you cannot choose your motor without considering the gearbox. Right? For every motor you choose, you have to pair it with a certain gearbox to achieve uh, the required torque at required RPMs, right? And so the way to do that is to say, well, for a given combination of motor and gearbox, start by plotting how much torque is available at each RPM on the lap. So, for example, this is for the endurance event, right? So, on the endurance event, in step 2, you had required torque and RPM. Now we're plotting available torque at each RPM on the lap, right? And again, we're plotting this for the motor plus gearbox. Now, once you have that, the natural question is, well, do I have available torque that is more than required torque at all speeds, at all times, right? If my available torque is less than required torque at some point, then either I have to change the motor or change the gearbox or both, right? So it is important that your motor plus gearbox together can deliver the torque that you're going to need to achieve your performance goals that you defined in step 1, right? Now, of course, the important thing in this is as a good engineer, you should keep a margin of safety, right? So your motor should be slightly oversized, or motor plus gearbox should be slightly oversized, so that you're delivering a little more torque, 20%, 30%, 50% more torque than required, right? Because again, motors have efficiency regions where they're more efficient versus less efficient. You can't run your motor at sort of peak torque at all times, right? So make sure that you keep some sort of margin of safety, right? Now, once you've plotted this available torque at each speed for the motor plus gearbox, right? Now, the kinds of things you should worry about or think about when you're selecting the motor, right? Is first of all, like I said, several teams often mention that, well, peak torque or peak power is we need minimum this, right? Well, that alone is not the important thing. You should also worry about things like basic things like voltage and current, but also power to weight ratio, right? Are you choosing a motor that is very heavy, right, for the amount of power it is delivering? Are you choosing a motor that is going to require external cooling? Because if you require external cooling, that means you require power for that external cooling, which means you're going to eat up your battery to power that, which means you're going to need a bigger battery, right? So these are all constraints that you have to consider while selecting your motor, right? Now, the important thing here is once you fix a motor, right? The motor at a high level is something like, this is like a 30 kilowatt motor that operates at 230 volts or 250 volts or 400 volts or something. The moment it's a 30 kilowatt motor operating at 300 volts, that means your rated current is 100 amperes, right? So once you pick up a motor, that already defines the battery pack voltage and the battery pack current rating, right? Often, I mean, one of the things that you have to think about is, should you use a high voltage low current motor or a low voltage high current motor, right? And so, for example, at least the teams that I reviewed in the last couple of years, I saw voltages all the way from 72 volts to 630 volts, right? Which is a very wide range, which goes back to my initial point about a large design space. You could choose something that is as low as 72 and as high as 630, right? Now, what is the trade-off, right? The trade-off is if you choose something that is low voltage and high current, the first thing that a good electrical engineer will tell you or should tell you is that your losses in the motor and everywhere in the circuit are proportional to square of the current, right? They're literally called I square R losses. And so if your voltage is low, your current is high. If your current is twice, then that means your losses are 4 times, right? So in general, it's preferable to have a higher voltage but low current, right? Now, the downside generally of higher voltage, of course, is that you have to worry more about insulation, right? You have to worry more about sort of your safety circuits, right? Electrical shock from a 48-volt system versus electrical shock of 250 volts is a very, very big difference. One will take you to the hospital, right? So you have to, when you're working with high voltages, you have to be extremely safe. You have to worry a lot about your safety circuits, your safety precautions, the way you design, the way you fabricate things, right? But on balance, given everything, a high voltage, low current system is probably turns out to be better than a low voltage, high current system, right? And then what you could do is you could pair a motor with a slightly low power, high voltage, with the right gear ratio, right, to get the required torque, right? So don't. So for example, if the limit on your motor power is 80 kilowatts, you don't necessarily have to get a motor exactly of 80 kilowatts, right? You can get a lighter, cheaper motor that is say only 40 kilowatts, right, but has the right kind of torque speed characteristics, and couple it with a high gear ratio to solve your problem, right? So again, I mean, bigger isn't always better when it comes to motor selection, right? That's sort of the big sort of learning, in this step. Now, once you've picked a motor, right? Like I said, the next natural step is to say, okay, well, what kind of accumulator or a battery pack will power this motor, right? And so first of all, the moment you decide a motor, your motor voltage is fixed, which in turn determines the battery pack nominal voltage. Okay. Secondly, in order to know how big a battery, so again, how do we talk about battery packs is we say something like it's a 72 volt, 5 kilowatt hour battery pack, right? What does that mean? What that means is that the rated voltage is 72 volts. So if your motor, for example, is a 72 volt motor, then your battery pack has to be a 72 volt battery pack, right? Now the 5 kilowatt hour, what that means is this is the total energy that the battery pack can deliver under normal conditions of operations, right? So then you have to look at your lab simulations or your calculations to say, is 5 kilowatt hour enough for my vehicle to drive around the lab so many times, right? Or whatever is the total amount of energy you're going to need across all your events. And so that determines the size of the battery pack. So the motor decides the voltage, the total energy you need decides the energy of the battery pack. Again, be sure to keep margins of safety. And then something like the acceleration event is where you're going to draw the most amount of current, right? For 3, 4, 5 seconds, you're going to go, you're trying to operate at peak torque, which means you're trying to operate at peak current. So your acceleration event gives you sort of the peak current requirement, right? Now, once you have these numbers, right, then comes time to say, okay, well, in order to build this battery pack, I'm going to have to select a set of cells, right? Like I said, I mean, I don't want to go into sort of fundamentals of cells, but there are different kinds of cells, both in their geometry, in their chemistry, and in their C ratings, right? So C rating says what is the maximum current I can draw from a cell as a function of what its capacity is. So if a cell has a capacity of 10 ampere hours, and maximum I can draw is 30 amperes, then it's called a 3C cell, right? 30 divided by 10. There are cells that give you high C rating, which means that the max current you can draw from them is significantly higher than their capacity for a short period of time. And there are other cells that are low C rating cells, right? High C rating cells, as you can imagine, are expensive, right? So depending on how much your budget is, right, you have to balance whether you get a small number of high C rating cells or you build larger pack with low C rating cells that is still capable of delivering the same amount of current, right? And this sort of, right, so we started with high level specs of the battery pack, and then the next step comes is like, what cells do we pick? And depending on what cells you pick, it essentially gives you sort of a grid of cells, right? The grid is because you put some cells in series and some in parallel. You put cells in series to achieve the nominal voltage, right, which the motor operates at, and you connect cells in parallel to give you the amount of current, peak current that you require for the acceleration event. Right? So you have this sort of series parallel grid of cells. Right? Now, one thing to note here is that it is generally easier to work with a small number of large cells rather than a large number of small cells. This is one place where there is a difference between working on a production vehicle that has to go, that say a Tata or Mahindra someone might build, versus a student competition vehicle which doesn't have to run for tens of thousands of kilometers, right? Durability wise, large cells may not be that great, but for your purpose, for this competition, large cells are easier to work with. And so it's preferable to build um, a grid out of large cells like prismatic or pouch cells rather than small cells. For example, if you build these with cylindrical cells similar to AA and AAA cells that you get off the shelf, one of the problems with that is that you have to do spot welding on it, right? So you have to weld it using a sort of expensive welding machine, and that's not available everywhere. So this is the kind of considerations you have to think about before you simply jump into saying, okay, well, let me ask the next guy what cells they're using, and we're going to use the same cells, right? You should think carefully about cell selection as well. And then, so once you've done this, right, then the next question is, well, and this is another place where electrical engineers have to work closely with mechanical engineers, right? And so this is another thing where the choice of your battery pack layout and your components will in turn affect the amount of heat your battery pack is going to produce inside it, right? The choice of the cell. So something as simple as internal resistance of a cell, which is written on the data sheet of every cell, right? As a good electrical engineer, you should worry about the internal resistance of a cell. Why is that? Because again, the amount of heat generated inside the cell is going to be I square R, where R is that internal resistance. So if you pick a cell that has 3 times the internal resistance, you're going to have 3 times more losses, and those losses will produce 3 times more heat, which your mechanical engineering friends have to then worry about how to dissipate. Right? So the thermal analysis, thermal management of the battery pack is something that requires some ideas, sort of some analysis or concepts from heat transfer and so on, right? You have to worry about how much heat do you have to extract, and whether that can be done with active cooling or passive cooling, right? So step 1 is choose components that will produce less heat. One way to do that is to have lower current. Another way to do that is to have cells with lower internal resistance, right? Now, once you do that, then you say, okay, this is the amount of heat that has to be extracted out of the battery pack, right? That calculation typically requires some sort of a simulation that someone has to run. Now, once you do that, then you have to make the decision about active cooling versus passive cooling, right? So what does active cooling mean? Active cooling typically means that you have a motor or a pump that pumps in a fluid through the battery pack to cool it, right? That fluid is typically glycol plus water or something like that, right? So again, if you have that, then your circuit becomes more complex. The pump sucks up some more energy, stuff like that. Right? So it's more complex, more expensive, and more energy consuming, right? So see if you can use passive cooling, right? If you chose your components properly, you wouldn't produce a lot of heat, and if you don't produce a lot of heat, then you may be able to get away with passive cooling, right? One way to do passive cooling is to be clever about how you redirect ambient air through the battery pack or or around the battery pack. Another way is to use phase change materials, PCM, or thermal pads or gels. So that's another way that you can find you can do what's called passive cooling, meaning you're not actively taking heat away. You're simply making it easier for heat to be dissipated through the casing of the battery pack, right? So these thermal issues are very important. It's another critical place where Electrical engineers and mechanical engineers have to work closely to to first identify sort of how much heat needs to be extracted through simulations, then come up with ways of passive cooling or active cooling, and then to keep, to run more simulations to make sure that um, that sort of cooling method is actually effective, right? It's actually extracting the heat you would like to extract, right? Um, the last point I want to make is about um, choice of a battery management system. Right? Here again, it's a relatively new sort of field. It's a relatively nascent market. So there is a wide variety, and they're very dubious quality. So be careful about what you're going to use, where do you source it from. Talk to other people, make sure that BMS is something that if you're going to buy from somewhere, that other teams have had experience using it, right? If you're not going to buy from somewhere outside, you better have good reasons for it, right? In the past, we have seen teams who have built their own BMSs, but a lot of these teams started building their BMSs 3 to 4 years ago, right? And some of these are top teams in the competition. They started it 3 or 4 years ago. Over time, they have gotten it down to be pretty good. If you're starting today, the same constraints may not apply to you. So you may not have to write a BMS from scratch or build a BMS from scratch. Building a BMS is not easy, right? Anyone who tells you that it is easy is either lying to you or doesn't know enough, right? So be very, very careful about building something as critical as the BMS by yourself, right? Particularly, I mean, I know several people who are in the business of building battery packs who've had accidents of various magnitudes, right? With thermal runaway or with small explosions in the battery box, stuff like that. And these are people who are supposed to know what they're doing, right? So building a BMS, building a battery pack is not a joke. Uh, take it sort of very, very seriously, particularly if when you're working with high voltages. And so this is sort of my tip about. I mean, I'm not spending enough time in this talk about safety circuits and so on. There is a lot of literature on it in the Formula Bharat rule book and so on. If you have questions, reach out to us. We'll direct you to the right places. But take electrical circuit safety very, very seriously, and take it seriously both in terms. So your choices of circuit breakers, choices of fuses, choices of keeping margins of safety, both in the way you design the powertrain and also in the way that you actually fabricate things, right? There is a lot of room to make mistakes, to be sloppy during assembly and fabrication of the battery pack. So it's very critical, like to take these things seriously. These are not things that you have to deal with a IC engine, right? IC engine sort of only is harmful when it's actually working. When you're assembling it, it's like a dead thing, right? That's not true of a cell. A cell is live, right? If you short it, it will blow, right? And so be very careful with when you transition to building high voltage electrical systems. Consult people in your respective electrical engineering departments. Consult people outside. Be very careful. Be sort of always be very safe, right? Like take it very, very seriously, right? So this was sort of the rough 4-step process, right? Let's quickly go over what we talked about, right? Start with your performance goals. Start by asking yourself, well, what do I want to achieve? What do we as a team want to achieve in this year's Formula Bharat, right? Write it down in as precise a way as possible, right? Once you have these performance goals from your vehicle for each event, right, that should translate into technical requirements on your electric powertrain in terms of torque, RPM, current, and so on, right? So translate those performance goals into technical requirements, right? Once you have that, particularly requirements around torque, then you should do your motor and gearbox design, or motor selection and gearbox design together, right? And the goal should be to be able to deliver the required torque at the required RPM at all times, right? Like I mentioned, be careful with motor selection, because once you fix a motor, it fixes your battery pack voltage and current ratings. So in other words, it also fixes your losses, because once the current is fixed, then I square R is fixed, right? So you cannot then, I mean, you're going to produce a certain amount of heat, you're going to be you'll have certain amount of losses by simply choosing the motor you're choosing, right? So be careful about sort of high voltage, low current versus low voltage, high current kind of trade-offs, right? Once you pick the motor, focus on design of the pack, focus on sort of your energy and endurance, or energy and peak current requirements, right? See whether you can use a small number of large cells, right? They're easier to work with. They can even be connected into a pack by hand. You don't need a welding machine for it, right? And then worry about thermal management. Worry about sort of simulate as well as you can the amount of heat produced within various parts of the pack, and how much of it has to be dissipated, how quickly, right? Sort of the final thing here was to be careful about electrical safety, right? Which is again something that you don't have to worry as much in IC engine vehicles, and so worry about it a lot, both in the design of your electrical circuit and also during assembly and fabrication of every component, particularly the battery pack, right? So with that, let me give you some sort of final thoughts here, right? And this is overall for your vehicle building. I mean, I know, I'm assuming that most of you have built a Formula student vehicle before, and that was most likely a IC engine vehicle, and that's why you're attending this talk, because you want to transition now to electric, right? So the first sort of high level thing I want to leave you with is try to design the entire thing with experimentation in mind. And what I mean by that is that you're almost certainly not going to get everything right or even complete in the first attempt. All right. And so you should almost think of it as, I'm going to take 3 iterations or 4 or 5 iterations to get this circuit working properly as expected. And to do that, I don't necessarily know all of the things that I'm going to use in my final thing. I don't know what fuses, what circuit breakers, what gauge wires I'm going to use everywhere. So try to make it easy to swap components, swap parts, swap wire harnesses, fuses, other things, and quickly check performance, right? So design your circuit, design your thing in small chunks that can individually be experimented with, individually be tested for various performance parameters, right? And where iteration is made as easy as possible, right? This is very important, right? Because if you're doing this for the very first time, you should almost say to, like, every morning you should say to yourself, like, this is like, I'm not going to get this right the first attempt, so I'm going to work on it. This will change, and I have to make it easy for me or my team to change components, change things, experiment with things, right? Don't sort of cage yourself or restrict yourself into a particular design that you cannot get out of, even if you come up with good ideas later. So that's very important. The second thing, which ties back to experimentation, is measure everything. You can't improve what you don't measure. So from the very beginning, think carefully and think in great detail about instrumentation of every part of the electric powertrain, and possibly every other other subsystems of the vehicle, right? So what do I mean by instrumentation? I mean measure voltages, currents, temperature, pressure, acceleration, yaw, as many things as possible, measure it at as many places as possible, right? This will require sensors. This will require transducers. You'll have to go, buy these things. You have to put them in the circuit. Um, if you don't measure these things, you will not be able to improve them, right? One of the great things about an electric vehicle is you can measure things very, very, very precisely. And so one quick example or sort of story I want to talk about here is in the vehicle that we are building. When we assemble a prototype, assembling the brakes is always a problem, right? So you assemble the brakes can't be too tight, they can't be too loose. It's always a hassle. And so one of the things we know is how much current does our motor draw at no load, peak RPM, no load, right? So let's say it draws 6 amperes, right? Now, when we get a vehicle and it has the brakes on, we put it on stilts and run it at full RPM, again on no load, but this time with the entire vehicle, and check how much current it is drawing, right? If just the motor alone was drawing 6 amperes, and if the vehicle as a whole is drawing 13 amperes or 15 amperes, you know that the brakes are too tight. It is the brakes or the bearings that are causing the extra friction that is making the motor draw more current at the same RPM, right? So because we are able to measure electrical current precisely, from that measurement, we can tell you whether the brakes are too tight or too loose, right? And literally, I mean, this is something that we used to argue about, and now that we've started measuring it, now we know whether the brakes are loose or tight just by measuring current, right? So this is an example of something where, because it's an electric powertrain, you can measure things very precisely. You can measure currents, voltages, right? All of the sensors have, come with some voltages, and either the sort of output is usually current or voltage, and so you can measure them very precisely. And as you measure it, you will know even if there are 5, 10, 15% changes in performance, either happy changes or sad changes, right? Either changes for the better or changes for the worse. But you wouldn't know these things if you don't measure. So spend a lot of time and effort on instrumentation of the vehicle, particularly during design, right? Don't assume that you will get it right the first time. So if you're going to have to iterate, then you're going to have to measure each combination, each configuration, each choice, right? The third part is be very careful about build versus buy decisions, right? Don't build anything that you can buy off the shelf from the market, right? And this is slightly harder, like I mentioned early on, with electric components, because most electric components in the market are not meant for automotive, right? Most people don't understand things like C ratings and so on. There aren't that many people selling lithium-ion cells, for example. But you have to spend a lot of time and effort on sourcing. Don't give up saying, oh, like I can't find a BMS, let's just go build our own BMS. I can't get a HMI, so let's just build our own HMI or something, right? So try to build fewer things, because everything you build from scratch will fail multiple times, right? So if you say, okay, let's put together a team of 4 people, they will write a BMS in 6 months, right? I can guarantee you that will not happen, right? And right, so there is a certain amount of over optimism that almost all engineers have, right? And experienced engineers have. So you guys are not alone. I am not alone, right? And I'm as guilty of this as anyone. And there is a very natural temptation to say, let's just build this thing from scratch. How hard can this be, right? And so please resist that temptation, right? Spend more time to carefully look for ready-made, off-the-shelf things in the market, so that you don't have to build stuff from scratch, because everything that you build will not only fail by itself, it'll be doubly more sort of complicated to integrate it, right? Integration of things takes a lot of time and effort. So avoid building things that are some way available off the shelf, right? The last part, which I want to talk about, is tangentially related to electric powertrain, right? It is related. I mean, in general, if you're building a race car, race vehicle, you should obsess about weight. So I'm hoping that you guys already know this, right? The part where this is even more critical with electric powertrains is that electric components can be expensive, like particularly cells can be expensive, batteries can be expensive, right? And so instead of just sort of lazily saying, okay, if we're allowed to get an 80 kilowatt motor, let's just get the largest motor we can and we're done, right? It would be much better, both in terms of your vehicle itself, but also it'll look much better in your report of the vehicle, that you were able to cut down weight by 20% or 15% or 12% by carefully designing your vehicle, right? So obsess about every component and its weight. All it requires, or to a large extent what it requires, is you being creative and sort of obsessive about the weight of various components, right? And this is not specific to electric at all, right? You should obsess about the weight of your frame, and whether the frame can be done with 1.2 mm, aluminum versus 2 mm steel or something, right? So worry about the weight of every component. Find ways to shave off 100 grams here, 500 grams there, right? Every little thing counts, because that's the only free lunch. Because if you can reduce weight by 10%, then the same motor and same battery will give you better performance. Or you can get the same performance with a smaller motor and a smaller battery, right? So the reason this is valuable is because your motor and battery is what's both expensive, right? And also sort of hard to put together, right? And so once you fix your motor and battery, if you can lower your weight, then that gives you a free performance boost, right? That for which you have to spend nothing. And so that's one thing that you should sort of worry about a lot, because a lot of it comes down to just being creative and just being obsessive about the weight of individual components and what you can shave off. Right? So these were sort of my high-level parting thoughts on building, right? This is exciting for me to know that so many of you are interested in building electric powertrains, and I wish you all the best, right? Godspeed, enjoy the ride. The thing I want to mention here, which is critical, is that this is a competition. There is some amount of joy and pride to be had by winning the competition, but really what you should enjoy is the journey of starting from a clean sheet of paper and building a powertrain, building a vehicle that runs the way you imagined it will run, right? And the creative satisfaction in building it and the learnings from building it are the prize in themselves. That is why this is worth doing, regardless of the outcomes of the event, regardless of what you achieve in the event itself. So enjoy the ride, both as the ride of the vehicle, but enjoy the journey of going from a clean sheet of paper to a vehicle that runs the way you would like to. So thank you and good luck, and I'll see you at the speedway sometime in the future. Maybe not next year, but the year after. Right? Good luck.
Thanks, Pranav. We do have two questions that came in via the live Q&A form. I'll start with the second one. Since we have some time before the next speaker joins in. So the question is from Bhavya Parekh. If we keep the available torque greater than the required torque, isn't there a chance of crossing the traction limit and thus leading to wheel spins or skids?
So to be clear, available torque just means that this is the torque that the motor is capable of delivering, right? That doesn't mean that this is the torque that the motor that is being drawn, right? So to be clear, available torque doesn't mean that the torque delivered. It just means this is the capacity of the motor, right? So you want a motor that is capable of delivering, say, 100 Newton meters of torque, even if you only choose to draw 80 Newton meters, right? So whether the wheel spins or skids is a function of sort of the vehicle dynamics in some sense. It's not a function. I mean, the motor will not deliver any more torque than is required, than you ask for, right? And what you ask for is simply controlled by the throttle in some sense.
All right. And the other question, I think you probably answered it, but I'll just ask anyways. It's from Sai Kiran. How do we decide that we are ready for EV? Where do we start learning for an electric vehicle?
Well, so first of all, I mean, you will never be ready until you start, right? So I mean, ultimately, you have to know that you have a certain amount of budget, right, to start. If, for example, if you have an IC engine vehicle already and you don't have a budget at all to do anything new this year, then you shouldn't make any major changes to the vehicle, right? Then you make some small tinkering changes and you just like participate or whatever, right? So I mean, the first step has to be that, well, okay, this year we have enough of funds to, I mean, either from your college or from sponsors or your own money, whatever way you collect them, you have to have a certain budget to start. And in some sense, that is the only prerequisite, right? Beyond this, my guess is that several teams that are right now building IC engine vehicles are primarily composed of mechanical engineering students. There might be a few electrical engineering people, right? But overall, the electrical engineering component in an IC engine vehicle is much smaller. So one of the other requirements, so first requirement I said is money. The second is people, right? So are you going to have a commitment from electrical engineering students to spend time and energy building the electric powertrain, right? Because you're going to require a sizable amount of time and effort investment from them to work on this. So the first step would be to, once if you have the money, then go recruit a few friends of yours from electrical engineering, or people who know who know enough electrical engineering that they can build something like this, right? And from that point on, it's just about, there is a ton of resources about electric vehicle technology on the web, on YouTube, and so on. Don't spend a lot of time looking at sort of what Tesla is doing or what Volkswagen or Tata Nexon is doing or whatever. Instead, spend time looking at sort of DIY or hobbyist videos of people who are building electric bicycles or tricycles or small, golf carts, right? Those are vehicles where, first of all, because they're built by hobbyists, it's sort of easy to see what they're doing, and secondly, those circuits and those components are simple enough that they would roughly be similar to what you would need, right? Don't spend a lot of time getting sucked into the hype around large electric cars that are extremely sophisticated and extremely complex, and therefore, if anything, they'll just like scare you away, right? So spend a lot more time just learning the basics, right, of doing it. If you as a team have enough time, you could even sort of challenge yourself to build like a small electric bicycle in, say, 1 month, right? So take a regular bicycle, see whether you can retrofit an electric kit onto it and make it an electric bicycle in the course of 1 month, right? And that will give you a very clear, very nice sort of sense of what are all the individual components that go into electrifying the powertrain. And then, of course, you have to go build the actual vehicle. But other than that, other than money and people, everything else is just time and sweat, right? You work hard at it.
Okay, Pranav, we've got 2 more questions. We'll see how much we can do for time over here, and then you can take the live Q&A also on Gather.Town as well.
Sure.
So the next question is, what are your views on having regenerative braking and complicated things in the first time, or should you suggest that we proceed slowly? I think that's
Right.
what the question.
Yes. So first of all, you don't have to do too much for regenerative braking. Regenerative braking is something that often is a feature in the motor controller, and there are several motor controllers that come with it, right? You simply have to sort of make sure that or have some calculations around how much current will go back from the motor into the battery pack during regeneration, and whether your battery pack can handle it, right? Now, as a starting point, you can buy a controller that allows regenerative braking, but turn it off, right? So you can start with a controller that is capable of doing regeneration, but if you don't want to deal with it, just turn off the thing. Most motor controllers are configurable in that way. Turn it off, build the whole thing without regeneration, right? And then once you feel comfortable with everything else, then see whether you can turn on regeneration and what problems that might cause and how to fix those problems, right? So you don't have to do too much to enable regeneration. And all you have to do is like buy a controller that allows regeneration, and then as a starting point, you can turn it off and build something from there.
All right. And another question from Neelan DeCruz. Which softwares can be used to design and simulate the EV powertrain?
I mean, there are, so first of all, I mean, the wire harnessing and so on, you can do in SolidWorks, although you may not need it. I'm drawing a bit of a blank here. So, okay, I know that MATLAB and Simulink have very good simulation capabilities for, okay. So I guess the number one answer would have to be MATLAB and Simulink. They have very elaborate block level models of various motors, and so you can build the entire powertrain and do several kinds of analysis just there. And then if you know Simulink well enough, you can even build your own model and plug it into your powertrain. But that's one place where I would start. They're also generally very helpful with student licenses and stuff like that. And so it shouldn't be too much problem sort of getting started.
I was also going to add that after this session, there is a session by Prem from Zook in India on wiring harness design via their softwares available.
Perfect.
So Pranav, thanks a lot. This was a great session, and we had close to 110 participants during this time.
Wow.
So,
That's great.
So yeah, that is great. So Pranav, you're going to go, so to all our participants on Gather.Town right now, Pranav is going to meet you actually at Hogwarts Library. Pranav, Renita will be at Gather.Town waiting for you, and she will direct you to the private space at Hogwarts Library. And participants, if you have any questions for Pranav, please feel free to ask him as Pranav, thank you for dedicating your time and for your efforts for today. We really appreciate it, and really glad to have you back, with Formula Bharat.
This is exciting. I would love to do this again.
Awesome.
Right? I'll